Hello. Today in this video, we'll be talking about question one, part three of CSM week two worksheet. And this question asks, consider all complete undirected graphs on an even number of vertices. Prove that such graphs can be partitioned into n divided by 2 spanning trees that share no edge with another spanning tree. So before we tackle this problem, let's look at a couple definitions that we need to clarify. So consider this K4 graph, which is a graph of 4 vertices, all fully connected. This K4 graph is exactly the type of graph that our problem is asking for, as it is complete and it has an even number of vertices. However, there are two additional constraints that our problem offers. And this is that firstly, we are looking at these things called spanning trees of K4. So what exactly is a spanning tree of K4? A spanning tree is a subgraph of K4 that is a tree and also hits all the vertices of K4. Examples of spanning trees of K4 would be these two on the right. And as you can see, they indeed hit every vertice and are both trees. The second condition that our problem mentions is that these spanning trees should not share any edges. Examples of that constraint is on the screen, where these two spanning trees are both spanning trees, yet share exactly no edges. So now that we have these definitions established, let's go about actually proving the problem. The most straightforward approach to this problem would be induction on the number of vertices. Our base case will be the two vertex complete tree, which is simply this. And it is straightforward that such tree will only have one spanning tree inside it, which aligns with our formula of n divided by 2 when n equals 2. So now that we confirmed the base case, we then go on to the inductive hypothesis. Our inductive hypothesis would be simply that for some even k greater than or equal to 2, the k complete undirected graph can be partitioned into n divided by 2 spanning trees that share no edge with another spanning tree. Here, n stands for the number of vertices, so this could be rewritten as k divided by 2 spanning trees. And now with this inductive hypothesis, we want to prove or show that the k plus 2 complete undirected graph can be partitioned into k plus 2 divided by 2, or k plus 1 spanning trees that share no edge with another spanning tree. So how do we do this? Firstly, to prevent us from running into any buildup error, we will remove two vertices from this k plus 2th case. Removing any two vertices from the graph of k plus 2 vertices will give us a k complete undirected graph, just like our inductive hypothesis. Therefore, we see that we will have no buildup error, and we can safely add back these two vertices. And let's call these two vertices that we add back x and y. So now we want to add these two vertices to our existing k divided by 2 trees from our inductive hypothesis. And these k divided by 2 existing spanning trees from our inductive hypothesis can be expressed in such a way where we divide all the vertices inside our large complete graph into two groups, A and B. And each spanning tree of our big complete tree will have elements from A and B, all connected in some kind of arbitrary configuration that we are not sure. So in such case, we want to add X and Y to each set of these spanning trees that we already have. How could we do that? So one way to do this is by simply saying, oh, we want to connect X to some component within the A set, and we want to connect Y to some component within the B set of our spanning tree. And we can do this for every single one of our spanning trees. And in this case, we see that now we will have K plus 2 spanning trees for our inductive case. However, we do not want to have K plus 2 spanning trees. We actually want to have K plus 2 divided by 2, which is K plus 1 spanning trees. So then how exactly could we get this one extra missing spanning tree? The way to do this is by noticing, oh, in this example, we've connected X to every single A component, and we've connected Y to every single B component. So how about now we flip what we did and connect all Y's to our components in the A group and connect X to all the components in the B group. So this would look something like this, where we have some arbitrary Y vertex, and we, sorry, and we connect this to every element of A, and we have some X vertex, which we connect to every element of B. So we see that this will not have any shared edges with any of these spanning trees, as we have made no connection between Y and A in our K plus 2 existing trees case, and for X, vice versa. So now the only step we have left is to make this case a tree, because right now we see that we have two different groups and we want to connect them together to actually produce a connected tree. Now, how do we do this? We can simply add a edge between X and Y. And this would give us the extra tree that we are missing, producing exactly K divided by 1 spanning trees. And we are done with the problem.